Hello, students working on your own. Today we're going to be talking about section 5.17, Hund's rule and orbital filling diagrams. Remember, this presentation is exactly what you see from your CK12 packet. Okay? Like I said, it should be exactly what you see here, except it's in a PowerPoint. All right? So I'm working with my 5th period class. So let's get started. Hund's rule and orbital filling diagrams. Have you ever wondered what those load limit signs mean on a bridge? Who's going to help?
The sign above says that nothing over 5 tons is allowed because it will do damage to the structure. There are limits to the amount of weight that a bridge can support. There are limits to the number of people that can safely occupy a room, and there are limits to what can go into an electron orbital.
Thank you, Yalexia. So if you've ever gone on like a major bridge, like I'm talking like a real long bridge, like the Golden Gate Bridge, or I think the closest one that I've ever been to around here is the Port Isabel Causeway Bridge, right? The Queen Isabella Causeway, which is the bridge to go to the island. That bridge can only handle a certain amount of weight. Okay. And I don't think I've actually seen a weight limit on it, actually on it, but I'm sure there is a limit. There is a limit for just about everything. There's a limit every time you step into a elevator. There's even limits right now on how many people can occupy a restaurant, right? And right now, I believe it's only 75% capacity. So we don't even, even if you go to a restaurant right now during the pandemic, you probably have noticed compared to the way that restaurant used to be, um, there are now some empty tables where you cannot sit. Okay. So the same thing happens with electrons and orbitals. We learned earlier this week that one orbital, can only handle a maximum of 2 electrons. Each box, right? Each box that we're going to be watching and dealing with today, working with today, should technically only have 2 electrons. You can have less than that, but you can never have more than 2 electrons within one orbital. And Hund's rule is the beginning of our discussion today. This is the last of the 3 rules for constructing electron arrangements, and that requires it requires electrons to be placed one at a time in a set of orbitals within the same sublevels. So which sublevels are we talking about? We're talking about P, D, and F orbitals, okay? Because those 3 types of orbitals or sublevels have more than one version of itself, right? For the p orbital, you have 3 versions of that p orbital. For the d orbital, there are 5 different versions. And for the f orbital, we have 7 different versions. For today, we're only going to be working with the 3 orbitals for p. So we're only talking about the 3 versions of the p orbital, okay? So anytime you are working with a p, a d, or an f orbital, there's going to be more than one version. In the case of the p, there's 3 versions of the p orbital. There's the x version, the y version, and the z version. Z as in zebra. Anytime you are distributing electrons, you have to always, and it says here, it requires electrons to be placed one at a time in a set of orbitals, okay? And you have a picture that goes with that. You have here these 4 elements that all fall into the 2p orbital. Energy level 2, orbital p. For boron, it has one electron in that orbital. For carbon, there are 2 electrons. For nitrogen, there are 3 electrons. And for the fourth element, oxygen, you're going to have 4 electrons that need to be distributed evenly. Okay? In the case, and you got to remember, there's always 3 versions of your p orbital. So in the case of boron, you're going to distribute that 1 electron in your first orbital. I always like to use the analogy of your 3 best friends, right? Everybody has, really good friends. And in this case, we are talking about your 3 best friends. So we're going to call best friend number 1, orbital right here, number 1, we're going to call it Alexia. Orbital number 2 is going to be named Oscar. And orbital 3, we're going to call it America. Okay? So I got my 3 best friends, right? I got Alexia, Oscar, and America. Think of these electrons as like gifts or candies, whatever you want to think about. So in the case of boron, well, I only have 1 gift to give. So since Alexia is my first best friend, she's going to get the gift first. And I'm sorry, Oscar and America, I didn't have enough. In the case of carbon, I have 2 electrons to give out. Alexia, since she is my first best friend, will get 1. Oscar, as my second best friend, he will get the second. And I'm sorry, America, I did not have enough gifts this time for you. All right. If we're talking about the element nitrogen, nitrogen is in 2p3. So I have 3 gifts to give out, or 3 electrons, right? So electron number 1, Alexia gets it. Electron number 2, Oscar. And finally, I get to give America 1 electron. Okay? If I'm talking about oxygen, which has 4 electrons in the 2p orbital, well, Alexia 1, Oscar 1, America 1, and since Alexia is my first best friend, she's going to get a second electron. Okay? Now, why am I spreading out these electrons? Why? Why do I have to spread them out, miss? Okay, let's answer that. This will minimize the natural repulsive forces that 1 electron has for another. All electrons have a negative charge, guys. So there's remember, like charges always push away. If you have opposite charges, they get attracted to one another. In the case of negative and negative, even if I want to put them together, they're going to naturally push apart. So this is that repulsive force that they're talking about. They are basically want to push away and get as far away from each other as possible. So this is what I mean by my 3 orbitals. I have to put 1 electron in the first, my second electron in the second, and my third electron in the third, so that I can minimize that push away that these electrons have. Now, once all of my orbitals have the same amount of energy, right, because they each have 1 electron, then if I have extra electrons after that, well, then I start doubling up. So then I give 1 to Alexia. And then if I have another, I give it to Oscar. And then if I have another, then I give it to America. Okay? And there's a rule. There's a rule for this. Okay? And it's known as Hund's rule. Hund's rule. Hund's rule states that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. And that's what we've been doing. If you are distributing, if you are giving out your electrons 1 by 1 in each orbital, you are following Hund's rule. If you put 2 electrons in the first one, 1 electron in the second, and leave that third orbital empty, you're not following the rule. Okay? You have to give them out evenly. 1, 1, 1, 2, 1, 1, or 1, 1, 1, and then 2, 2, 2, whatever it is. It all depends on where your element is. That is what tells you how many electrons you have. And if you go, and I'm going to go out of Pear Deck real quick. If you go to this, you remember, you have a periodic table that shows these electrons, right? If you're talking about beryllium, well, it says that there's 2 electrons, but you're in the 1s orbital, so you don't really care. But once you get to that 2p orbital, the 3p orbital, you got more than 1 orbital. In the case of aluminum, well, you just got 1 electron. So you're only going to put it in the first one. But if you're talking about chlorine, 3p5, right? Energy level 3, orbital p. I got 5 electrons because it has a 5 in the corner. I'm going to give 1 to Alexia, 1 to Oscar, 1 to America. That's 3. I got 5 total, so I got 2 more to give. I'm going to give the second one. Alexia gets a second one. Oscar gets a second one. And I'm sorry, America, I only have 5. She doesn't get that second electron. Each element tells you how many electrons you are giving out. And in this periodic table, the number on the right side is the number of electrons for that element. Okay? So Hund's rule. You must equally distribute. You have to give 1 electron into each orbital before you give a second. That's one part. Now, there's a second part to Hund's rule, that each of the single electrons must have the same spin. And what do I mean by spin is they have to all face up. They all have to face the same direction. Okay? In this case, for nitrogen, all of these arrows are pointing up. I cannot have Alexia pointing up, Oscar pointing down, and America pointing down. That's not it. They have to have the same spin. Same spin means same direction. If Alexia is pointing up, Oscar needs to point up, America needs to point up. If any of these single electrons are pointing down, I am not following Hund's rule. I'm breaking it. Okay? Now, once you have your single electrons and you add a second electron to that orbital, they must be in opposite directions, right? Because yesterday we learned there's a positive spin going forward and a negative spin going the opposite direction. So you have to have one pointing up, another one pointing down. I should never see arrows in the same box pointing both up or both pointing down in the same box. They must always be opposite. So Hund's rule says 1 electron per orbital before a second, and that the single electrons, 1 in each box, has to face the same direction, either all of them up or all of them down. Usually they're all up. The figure below shows a set of 3p orbitals filled with 1, 2, 3, and 4 electrons. We already talked about it. True or false? True or false? Hund's rule states that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron, and that each of the single electrons must have different spins. True or false? America says true. Read it carefully. It's a very long statement. Read it carefully. It's a very long statement. Mario says false. Sorry, guys. I got 4 students in Pear Deck. 2 students have answered. Let's see what they picked. Alexia says true. 2 people in Pear Deck said true. Oscar, what do you think? You've been real quiet today, Oscar. True or false? Oscar, Is this statement true or false? Hund's rule states that orbitals of equal energy are each occupied by one electron before any orbital is occupied by the second, and that each of the single electrons, right? Each of the single electrons must have different spins. So Alexia will point up, Oscar will point down, America will point up. Is that true or is that false? All right, so we got 4 truths, 1 false. I'm sorry, that's 5 truths and 1 false. Excuse me. That is false, guys. Look at it. Hund's rule states that orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second, and that each of the single electrons must have the same spin. Remember, if I got single electrons, Oscar, Alexia, America, they must have they must have the same spin. All 3 of them have to point up. Be careful, guys. I tricked you. Okay, now we're talking about orbital filling diagrams. So orbital filling diagrams are the same as electron configuration, except the orbitals are boxes and the electrons are arrows. An orbital filling diagram is a more visual way to represent the arrangement of all the electrons in a particular atom. In an orbital filling diagram, the individual orbitals are shown as circles. Mine are usually squares. They're not circles. And orbitals within a sublevel are drawn next to each other horizontally. Each sublevel is labeled by its principal energy level and sublevel. Electrons are indicated by arrows inside the circles, squares. An arrow pointing upward indicates one spin direction, while a downward pointing arrow indicates the other direction. The orbital filling diagrams for hydrogen, helium, and lithium are shown in the figure. All right, so this is orbital diagrams for the first 3 elements on the periodic table. Hydrogen, helium, lithium. Element number 1, hydrogen. Element number 2, helium. And lithium, element number 3. Now, if you look at the periodic table that we have, the electron configuration periodic table, you'll see that all 3 of them are in the s orbital. So there's only one version of those, right? S orbital, there's only one in the first energy level. In the second energy level, there's only one. So we don't have to worry about Hund's rule. The only thing that we have to worry about is making sure that those electrons are pointing in opposite directions, okay? So here, hydrogen, it has 1. There's your 1 electron. Helium has 2. Those are your 2 electrons, one pointing up, the other pointing down. So that's like one going forward, the other one going backwards. Lithium has 3 electrons. Since the first energy level is already full, it has 2 electrons. That third electron that lithium has to go in energy level 2, orbital S. Okay? Remember, guys, I should never see one box with arrows pointing up or arrows pointing down. Both of them. There's always 1 and 1. One goes up, the other goes down. Now remember, I can never have more than 2 electrons in one box, in one orbital. I can have less, but never more. Remember that when you see the next slide. You have orbital A. You got 3 diagrams, orbital diagrams, A, B, and C. All of them are wrong. Tell me what is wrong with A, what is wrong with B, or what is wrong with C. Pick one. I'm gonna assign 3 or yeah, Alexia. I want you to try letter A. See if you can figure out what's wrong with it. Oscar, I want you to try out B and letter C. I want Mario to try it out. See if you can figure it out, Mario. So A is Alexia, B is Oscar, C is Mario, and the rest of you guys pick whichever one. You're supposed to type out your response. You can type it out or you can just come off mute and tell me what's wrong with it. I'll give you some time to think. I need to finish my water anyway. You know what's wrong with one. So, Oscar, you were doing B. You ready to talk about it? Come off mute and tell me and help me discuss it.
I know what's wrong with number 1.
You know what's wrong with letter A, B, or C? Which one are you talking about?
With A.
But I asked you to do B. Yeah, Alexia's doing A.
Oh, okay.
America, you got A. Okay. All right, yeah, Alexia, if you see what's wrong with letter A, you can come and talk about it already. Or you can type it up. Whatever's easier for you, yeah, Alexia. America, you know what's wrong with letter A? What's wrong with letter A, America? You're still figuring it out. Okay. Look at each box individually. Two S. Okay. America is talking about 2S for letter A, okay? So we're looking here at 2S. Okay? She is saying that the arrows are pointing up. Should I have two electrons with the same spin? Is this correct? Should I have arrows pointing in the same direction, meaning both of them have the same spin? Is this possible? Should I have arrows both pointing up? No, right? I should have one arrow pointing up and the other one pointing down. Excellent, right? Because that means one's going forward, the other one's going back. Very, very good. Very good, America. Okay, Oscar, B. What do you see that's wrong with it? 2p has 3 arrows. Okay. 2p has 3 arrows. Okay, so the first orbital is okay. I got 2. The second orbital is okay. I got less than 2, but okay. But look at orbital 3. It has 3 arrows. That means I have 3 electrons in orbital 3. Should I have 3 electrons in this third box? Definitely not, right? No. Thank you, Oscar. No. This third arrow, where does it belong? Where should it be, Oscar? Where should this third electron be? in the box in the middle. Very good. It should be right here. And what direction should it be pointing? Down. Excellent. It should be pointing down. Very, very good. Very, very good. Does everybody else agree? I agree. Excellent. Great job, sir. Mario, I believe I asked you to look at letter C. Is there anywhere that you want me to start discussing? America agrees with Oscar. Excellent, America. Okay, come on, Mario. Do you see anything wrong with letter C? Start at the beginning. Mario, does this box for 1s, does this orbital look okay to you? 1s. Mario, are you there? Not listening, Mario. Okay, anybody else want to help me out? Anybody else want to help me out, please? Is there anything wrong with 1s, guys? Is there anything wrong with 2s? Is anything wrong with the first two orbitals? No. Okay. What about 2p? Is anything wrong with 2p? Is there anything wrong with 2p? No. What about 3s? 3p needs arrows. Okay, let's look at 3p. I don't think it needs arrows. I just think that one of these has... Now, remember, Hund's rule says if you have single electrons, right? If you got your first best friend, you got Yalexia, Oscar, and America. That means each one has one electron, right? If I got an arrow in each box, that means I got electrons in for each. But they're single electrons. Should this arrow's okay, but should this second arrow, should this second orbital have a downward pointing electron? Should this electron be pointing down? No. Oscar says it should be up. That's correct, sir. This second orbital should have an arrow pointing up. Very, very good. Remember, Hund's rule says single electrons must have the same spin. Remember, we indicate spin by the way if it points up or if it points down. If your first arrow points up, every single electron in all the other orbitals should be pointing up. Very, very good. All right, this is our final slide. We're at the end, almost at the end of our discussion. According to Aufbau's process, sublevels and orbitals are filled with electrons in order of increasing energy. Since the S sublevel consists of just one orbital, the second electron simply pairs up with the first, as in helium. The next element is lithium and necessitates the use of the next available sublevel, the 2s. Okay, so they have helium, 2 electrons, they go in the 1s. But for lithium, I got 3 electrons. My 1s is full. I cannot add a third electron into that orbital. It has to move into the next orbital, which is 2s. Very, very good. Okay. The filling diagram for carbon is shown in the figure below. There are 2p electrons for carbon, and each occupies its own 2p orbital. All right. So I'm here in my electron configuration. I find carbon. He's in the 2p orbital. And look at in the corner on the right, it says that there's only 2 electrons for carbon. Okay. So if I have my 2p, there are 3 best friends. Alexia got the first electron. Oscar got the second electron. I didn't have anything left for America. Sorry, America. Oxygen. All right, let's go to our electron configuration periodic table. Oxygen is in energy level 2, orbital p, and according to the box, there is 4 electrons that have to be distributed. 4 electrons, according to this guy. All right, so I go to 2p. I got 3 best friends. Alexia gets 1. Oscar gets 1. America gets 1. They're all pointing in the same direction. That's great. Alexia, since she is my first best friend, she's going to get that second electron. All right, almost done, guys. Almost done. All right, this is a challenge one because technically I haven't shown you how to do this, but let's see if you can, okay? As a class, we're going to do it together. So no, if you want to try it on your own, that's great. Or if somebody can come and give me the answer and post the answer, that's great. I'm going to give you a little bit of time, but we can discuss it as a class if it's necessary. What element is being represented below? So you don't really need to know and look at all the other orbitals that are already full. You need to go to the last orbital and look and see what's there. So if I go to the last orbital, I'm in energy level 3, orbital P, and I'm looking for the element that has 2 electrons. Go to energy level 3, go to orbital P, and find the element that has 2 electrons. What should that be? If this wasn't here and I had to stop and this was the last one, 3s2, well, I would go energy level 1, energy level 2, energy level 3. There's my s orbital. Okay, what element has a little 2 in the corner? In this case, it would be magnesium. But I'm not looking for magnesium. I'm looking for energy level 3, orbital P, and the element that has a 2 in the corner. Anybody see it? Does anybody see it? Does anybody see it? What element lands or is in 3p2? What element will I find 3p2 in? Oh, I got a response. All right, let's check it out. Let's give them a little bit of time. Let them think. And then we'll check it out. Let me have some more water because I need to finish this water before I leave or before lunch. All right, let's check it out. Let's see if they're done. SI. Who did this one? Who did this one? How did you get SI? Who did that one? Who got it? Oscar? Okay. How come you're not unmuting, Oscar? Usually you unmute. Okay. So he found energy level 3. He found orbital P. So we have 1, 2, 3. Okay. But I'm not talking about orbital S. I'm going to orbital P, which is all the way to the right. So here's 3p. I got 1 all the way to 6. I'm not looking for 1. I'm not looking for 6. It says here, I need to look for number 2. All right, so here's 3p. Here's number 1. You can see it in the corner. Here's number 2. Si is your element. That is silicon. That is silicon. Very good, Oscar. All right, you got your video. Let's watch it real quick. It's only about 2 minutes long, and I'm gonna cut it off after he finishes doing what he does.
300 for that in 2000.
I hate commercials. Oh, heck no. Skip it. Skip it. Oh no, is my internet lagging? Okay.
Now, we've done the electron configuration. Now, you see these little boxes here? These represent the electron orbitals for each one of those sublevels that we have here. We're going to fill them in. We call these electron box diagrams,
What's going on?
where we physically show the electrons within each one of these orbitals. Now, we're going to say we start out with 1s. How many does s hold? It holds 2. And remember, I told you they have to spin in opposite directions. One spins up, the other one spins down. That's 1s2. We can then move on to 2s following off-bow principle, because we have to fill in the lower orbital first before we move on to the next one. So this one also has 2, 1 up, 1 down. Now, in 2p, we have 5 electrons. But here's the thing. All 3 of these electron orbitals, all 3 of them are 2p orbitals. So they all have the same exact energy.
Okay, so he is working with fluorine. He's already come up with the electron configuration. So he's going to fill in all the boxes, and then he needs to distribute 5 electrons into that 2p orbital. He's already filled in the 1s. He's already filled in the 2s. Let's watch how he does that 2p orbital.
And we're going to have to follow Hund's rule to correctly fill it out. Hund's rule states that electron orbitals that are degenerate, so remember that word, degenerate, are first half filled before they are totally filled. Degenerate just means that they have the same amount of energy. And we know that these 3 electron orbitals have the same energy because they're all 2 orbitals and they're all p orbitals. So they're all 2p orbitals. So we're going to half fill them first. So we'd say up, up, up. You half fill them first. And you do this because they all have the same energy. Then you loop back around. Down, down. That's how you would fill out the 2p. So just remember that. When you're dealing with degenerate orbitals, they have the same number, they have the same letter, therefore they have the same energy. You half fill them first before you totally fill them in. Come back around and start filling them down, pointing down. 1s and 2s are not degenerate. They may have the same letter, but they definitely don't have the same number. One is 1 and 1 is 2. Because they have different numbers, they have different energies.
All right. Thank you, sir. All right. So that's just another example of orbital diagram. All right. So let's conclude our discussion. In summary, Hund's rule specifies the order of electron filling within a set of orbitals. Orbital filling diagrams are a way of indicating electron locations in orbitals. And your review questions. Number 1, state Hund's rule. Number 2, what is an orbital filling diagram? And number 3 and 4, they're asking you, is the diagram in the figure below correct? And explain your answer.